So today I'll be talking about how to perform Bayesian inference for random fields, let's say in a fast and quote-unquote valid way, via the Debiased Spatial Whittle likelihood. So this was work that I did primarily during my PhD, and several co-authors, Arthur, Matthias Villani, Matthias Quiros, and Robert Comp. So let's get started. So the outline of this talk will go as follows. First, I just want to introduce some kind of motivating real data examples, kind of get a feel of what kind of spatial data, what spatial data is, and what spatial data we'll be looking at in this talk. We'll look at the model and the kind of how to estimate these models. We'll talk about first the Whittle and then the Debiased Whittle likelihood. And I put that first just to kind of introduce it. And then we'll talk about the frequency domain kind of approaches, and then kind of how to make these adjustments, use these adjustments to perform valid inference. And then we'll circle back at the end and look at these applications that I've motivated the talk with. Oops. So to start with, here is what we call photosynthetically active data. So this is essentially radiation data. It's a satellite image of the Earth. And you can see what it does is that it captures a certain range of radiation, which comes from the ocean, so from the water. And what you see here is that you can see the continents outlined. Okay, this is all missing, right? This is primarily over water. And you can see that there's large kind of areas of kind of black. So the black is just missing over the ocean as well. So that's due to most likely cloud cover. And the idea is that we want to kind of see how the spatial structure varies with this radiation. So this radiation data is kind of a marker of how the kind of the ecosystem, the ecological life, kind of what state it's in, if there's abundance or not of this radiation. Here's another example. So sea surface temperature. So imagine you just took an image over the Pacific Ocean. Okay, on the left side is the actual raw data. So this is in degrees Celsius. You can see kind of on the lower latitudes here, it's kind of, you have a higher temperature, whereas you move up and you get slightly cooler. And after some kind of post-processing, you kind of, subtract the conditional mean and whatnot, we get these residuals. And this is kind of the data which we'll be looking at least in one of the applications. So this is kind of the data we have for our model we'll consider. Okay, another example. This is Venus topography data. So I think a satellite, a satellite goes to Venus. It takes a photo of the planet, and then you can see on the right-hand side, this is actually in meters. So the brighter areas are actually the elevation, perhaps not mountains but kind of higher areas of elevation of planet of Venus. Okay, so let's define some preliminaries. So a random field is a stochastic process which has a multivariate domain R of D. Okay, so in the time series case, right, you had a domain that's with time, so you had D equals 1. Here we're going to consider, at least in this talk, we'll consider D equals 2. So you have a kind of spatial multivariate domain. And of course, we can do D equals 3. You can do technically further than 2 or 3. But here what we mean is that X of S is the index or kind of the spatial locations. And again, we're going to assume that X has finite variance over each location. And so some examples of spatial data, again, what we've just seen, X is let's say like a latitude and longitude, spatial locations, points on a map, etc. And again, we can do spatiotemporal models, which is when you have space and then you add the dimension of time. So as time goes by. And of course, here we're just talking about essentially the univariate case of random fields, which is when the response, the data is just one variable. But you can have multivariate random fields. So example, if we had sea surface temperature and water and air temperature oh, sorry, sea surface temperature and like pressure, for example, then you'd have the response, the observations is more than one dimension. And again, applications, there's many fields. So, earth sciences, hydrology, sure. You guys would know many more applications than I would, epidemiology, etc. Okay, so again, let's just continue. So we have X has finite variance and is stationary. And here in this paper, in this presentation, we'll say we have observed this data on a regularly spaced grid. So the distance between the first row, point on the first row and the second row is equally spaced. And then we can define some delta, which is just the spacing between each of the points. And so that's a good. We can also, we can handle missing data and things as well, which we'll talk about later. And then, of course, if we just want the total number of observations, let's say we have 2 dimensions, then it's like a square or rectangle, and we just multiply the length and the width of the domain we have. So the product of the number of observations per side. Okay, and then of course, what we're interested in is this covariance function. So here we'll specify a covariance function. Imagine this is xs or x of t times x of t plus tau. That's in the time series case, the expectation of which. In the spatial case, it's the same, but you have these, instead of tau is like a scalar, now we have just the spatial lag, we call it the u, is just a vector. Okay, and so again, in this talk, we'll assume isotropic covariance function, which just means that the covariance between one point and some point in the distance is only a function of distance, but we can extend this work to anisotropic. So you get kind of different, different structures for the covariance for the random fields that you've observed. But here we're going to assume stationarity and homogeneities throughout the whole region we've observed, the data we consider. Okay, so here's just an example of some simulated random fields to get an idea of what we look at. So here, the C of theta of u, this is the covariance function. So we have different forms of the covariance function. We can see up the top that the rho is equal to 10 and the sigma equals 1. So I've just set these parameters. In reality, right, we want to estimate these parameters of the covariance function. Okay, but this is just realization. So you can see that on the top left, there's absolutely no structure, right? So each point, each pixel, each location is independent of one another, and you get no patterns, you get no spatial second order structures, covariance structures in this data. The one on top right, this is what's known as a squared exponential. So if you've worked with Gaussian processes, you would have seen something similar, at least in the form of this covariance. This is when you get very smooth, slow varying, persistent changes in the spatial process. Okay, and then again to bottom left here, you get slightly finer grained. You can still get a pronounced covariance structure, but you get kind of finely grained, more high frequency components in this data. And likewise, from the bottom right, this is called an exponential kernel, where you get very high frequency, more variation, the high frequency components with these different kernels. So again, the same parameters in each, but different covariance functions will give you different structures of the data. Okay, and so the previous covariance functions we've seen is actually part of a larger family known as the Matern kernel. So I forgot to put a reference here, I should have, but this was from I believe a Swedish statistician in the 60s. He did a lot of work with forestry data and point processes, and he kind of made this very general model of the covariance, which is the gold standard in spatial analysis today, spatial data. And you have 3 parameters. You have rho, you have sigma, you have nu. So the rho is like the range. So imagine the higher value of rho, then the less the covariance function will die off for points that are in some distance. So if you have a low value of rho, a small value of rho, then that will tell you how quickly the covariance function dies off. A sigma is just the amplitude, okay, like the amplitude of the process, so it's just a scalar here. And then nu is this parameter that controls this. They often call it the slope, that it controls the mean square differentiability. So you can see in this, going back to this case, the only difference between these three here is that the value of nu is changing. So for a really high nu, like nu is equal to infinity, you get these really persistent, slowly changing processes. Whereas when nu was a half a squared exponential kernel, you get very different behavior. So all these three covariance kernels are actually just specific cases of this Matern kernel. And if you've done some spatial analysis stuff, you would know that estimating this nu from the data is often quite hard. So sometimes people just fix it. And that's basically because taking gradients and things is quite hard because you have this special Bessel's function, Kp. Okay. So this is just, and again, this is motivating just our kind of data model because we want to perform inference, at least over the rho and sigma, Bayesian inference, which are the parameters of the covariance kernels. Okay, so imagine we've observed this random field. I'll denote it XS, X subscript bold S. And again, we're going to assume here the data is Gaussian, although we don't have to. We can perhaps talk about that later. But here we're going to assume that it's from a normal with zero mean and this covariance matrix, which depends on the covariance, which of course depends on the parameters data. Okay, and again, we don't have to actually assume a zero mean, so we can have covariance, we can have spatial covariance also with, like, let's say we have a mean of beta x bold x with some covariance, but in this dog we'll just assume that it's zero. But again, adding covariance in the conditional mean is not actually that problematic. It can be done relatively straightforwardly. And now the main problem with all this spatial stuff is that imagine you had, let's say you had 1,000 by 1,000 grid, right? So you had 1,000 times 1,000 data points. And what we have to do is that we want to compute the determinant, and we have to perform these, we have to solve these large systems of equations, which is very expensive. So in the general case, it scales as n cubed. And then for lattice data, which we have, it still scales to n squared times the one of the sides. So it's not trivial to even maximize this likelihood because it just takes too long to compute. But for irregularly spaced, you either run out of computation, or either you'll be waiting so long, or you'll just run out of memory. So it's restrictive in the memory and the time it takes to evaluate this likelihood. And again, obviously, now we assume that it's obviously Gaussian because we have the Gaussian likelihood, which may be inappropriate for some data. Okay, so here we're going to talk a little bit about the Whittle likelihood. And now what I want to do, usually when I'm speaking, I introduce the frequency domain first, and then I talk about the Whittle likelihood. But I want to do it the other way because I wanted, for the statisticians and data scientists, I want them to at least see the form of the Whittle likelihood, just to have it on the paper so they can see it first, and then we can discuss what are the components of the Whittle. So you can see that the Whittle likelihood is a sum. Okay, remember we had these large systems of equations. We have none of that here. Is a sum of these two components, the F, spectral density, and the periodogram. And before we talk about that, let's talk about the pros and cons about using this Whittle likelihood. So again, the Whittle likelihood is an alternative method of estimation for these models. So we can do time series, spatial data, temporospatial, etc. Okay, the really nice thing, the one that we'll use to our advantage, is the computational efficiency. So this is using the FFT. It's nlogn, so quasi-linear with the number of data points. This is very nice. You compare that to n squared times n, the second times n2, okay, or n cubed. This is very, very nice. It's also robust to the data generating process. So we won't talk about this too much today, but essentially, the Whittle likelihood doesn't specify a model for the time domain. It specifies a model for its frequency domain counterpart. So we don't actually need to assume Gaussian random fields, but in this talk we will. And this is a nice. The Whittle is very nice in terms of efficiency in kind of the lack of biasness you get in the 1D case or in the time series case. It's quite nice, especially if you have large samples. But what happens is in larger samples, first it introduces bias regardless of what dimension you're in. And it's a very inefficient rather, in high dimensions. So when you get to 2 or 3 dimensions, it becomes inefficient. And you introduce a massive amount of bias, which we'll have to address. And of course, the Whittle likelihood, as I said, it's an alternative method to estimate these models. It's actually an asymptotically equivalent method, i.e., if you have infinite amounts of data, i.e., if your rectangular grid you've observed, the data on increases on both sides, then this is actually asymptotically exact. So for the time series case, that's nice. But again, it's inefficient in larger dimensions. Okay, so again, I'm going to restate the Whittle. Here it is. Okay, and I'm going to actually be a bit more rigorous about how I define these things. So here, the sum is over what we call omega. This is the Fourier frequency. So if you've done a little bit of Fourier analysis, then this is just the frequency components. Here it's in 2D because we're talking about 2D data. Okay, we have 2 parts. We have the periodogram. This is quote unquote the data, right? So instead of the field X of S, we have the periodogram, the data component, and we have the model, quote unquote, the model. This is the spectral density. So this spectral density will encode all the information, the second order information of that covariance, or of the covariance function. So again, 2 components, and we need a little bit of Fourier analysis to define these properly. We'll start with the spectral density. Okay, so to estimate these models, again, we can look to the frequency domain. Okay, and the idea is that we want to analyze signals or data or images in terms of its frequency component. So we can break down signals into its sine and cosine constituents, and we can analyze these as it makes up the variance. So again, if you've done any sort of signal processing or analysis, you would know the Fourier transform. Here I've defined it again in the multivariate terms. You've probably seen it at least in the 1D case. Okay, we have the Fourier transform and its corresponding inverse. And for a covariance function, then via Bochner's theorem, essentially the covariance function is actually the inverse FFT of this spectral distribution, right? And the spectral distribution is just kind of the derivative of the spectral density. So what we mean here, again, I'm not being very rigorous about the exact specifications, like, there's some technical limits, but we don't need to get into that in this talk. Essentially, if it's continuous, then the covariance function, C, or let's start with the spectral density. The spectral density is the Fourier transform of the covariance function. And so these are kind of a dual pairing. So as long as with certain restrictions, it satisfies these restrictions, you always get this one-to-one correspondence of the spectral density and the covariance function. So it's nice because these parameters you'll see will show up in the spectral density, the parameters that we're interested in that are in the covariance function. So that's the kind of model part. That's spectral density is what we use as a kind of model for its second order properties. And the discrete Fourier transform is again a discretized version. This is when you actually compute. You can compute this in a fast way via the fast Fourier transform in quasi-linear time, nlogn. And the periodogram is simply just the discrete Fourier transform of the process X of S. So you can see this is the data we've observed. We just introduced this kind of this gridding value, which is between 0 and 1. That's just to say if the data is missing or not, or we can do some tapering. But all we're doing is that we're taking the discrete Fourier transform of the data X of S. We're taking its modulus, right? Because it's a complex number. We're taking the modulus and we're squaring it. And this is the power spectrum. This is the periodogram. This is our new quote unquote data in the frequency domain. So just as a brief overview again, we have the data in the frequency domain known as the periodogram, the Fourier Transform, the DFT, and we have the spectral density, which is the kind of the model for its second order properties. Okay, I'll go over these briefly. So in the random fields case, we're assuming a continuous model over the domain. So what that means that we are sampling the field discretely at discrete time points. And so we actually get this kind of alias effect. So this is when you've done some signal processing. This is when you've sampled a continuous function discretely, and then you have to evaluate the spectral density on this infinite grid. It's another reason why the alias spectral density is actually it's not always easy to compute, because it's an infinite sum over the frequencies. Okay, what's nice about the periodogram is that it's actually in expectation equal to the spectral density. Okay, and for each periodogram, well, sorry, I should say asymptotically. That's important. Asymptotically, so as long as we have large enough sample size, the expected value of the periodogram is the spectral density, and it's independent. So at each frequency, this is why we get this sum, because we can sum over each frequency, because asymptotically for each frequency, these are independent. Okay, and then it's actually exponentially distributed. So this is why, if you've seen the log likelihood for an exponential distribution, this is why we have this form. This is why we have this form of the Whittle likelihood here. Okay, so again, we just have two components, main components, periodogram and spectral density. We're summing up over the frequencies because asymptotically they're independent. So we get this kind of nice form for the Whittle. The only issue is that while asymptotically this is okay, we need both ends to go to infinity, right? We have two dimensions, and one, the length and the width of our observation. So there's been some papers that studied the quality of the approximation, because again, the Whittle is still a finite approximation of the exact Gaussian likelihood. So Guillaume and Kent and Mardia, the 80s and 90s, have studied the approximation. This is in the frequentist sense. So if you look at the estimates of the maximum Whittle likelihood estimate, essentially in the 1D case, in the time series case, the bias you incur by using this Whittle approximation is okay, smaller than the standard deviation. In 2 dimensions, it's on the same order. So you incur some bias and some error when you look at the maximum likelihood estimates. And for 3D, the bias is large, so you incur a much larger bias as you increase in dimensions. And so there was this paper by Dalhouse and Kunj, who they showed that tapering. So if you just say, well, let's just use tapering because it's efficient, and that's okay, but you'll see that in finite samples even, you still get this quite pronounced bias, even though we have these nice asymptotic properties that we've described in the previous slide. You still get this bias in 2 to 3 dimensions. And as Bayesians, this is all frequentist stuff. As Bayesians, we're interested in the relative error. So we have the likelihood, the true likelihood minus the Whittle approximation divided by, so kind of the relative error. Then this converges at the rate of the smallest slide of probability. But again, these asymptotics are quote unquote slow, as in we need heaps and heaps of observations. But if you have even more than 1,000 points on each side, the data becomes too even large to store it in a reasonable way. Okay, so again, this is all that I've just spoken about previously is motivating what we call the Debiased Spatial Whittle. Okay, you can notice this is the same form as the Whittle likelihood, but there's one exception. It's not using the spectral density, but it's using the expected periodogram. So this has been done in a few papers, but more formally, it's been done in the spatial case. This paper, JRSSB, I believe, and then the time series case in the Sokolsky 2019. So what they've done is that they've replaced an asymptotic quantity, which is the spectral density, with the actual expected periodogram. And this is just some convolution of the spectral density and this is what we call a Fayok, so some triangular kernel at the time domain. Okay, again, this is still nice because we can actually compute the spectral periodogram in O of n log n time, right? This is just convolution theorem. So we can actually compute this quantity and the whole Whittle, the Debiased Whittle likelihood in an efficient way. And also we can still handle missing observations, right? So we have a bunch of missing points, or we have some kind of weird domain shapes. We can handle this very naturally still with the debiased Whittle. So the point of the debiased Whittle likelihood is to kind of eliminate this bias, the bias you incur by using the Whittle, which is from the spectral density, and it replaces that spectral density with the expected periodic ring. Okay, and so you may say, "Oh, that's great. We can just do that, and it's all good." But the problem is that this is still a frequentist. So these two papers that have formalized this, they have studied this in the frequentist sense, right? And what we know is that, well, as Bayesians, we want to make this Bayesian, but we know that in finite samples, the debiased Whittle likelihood, I'll denote as DWL, and even the Whittle likelihood, it's misspecified. So it's a misspecified method or model, because in finite samples, it's not. It's only asymptotically that it's exact. Unlike the time series case, which the approximation is quite good. In 2 dimensions, the approximation of the true likelihood isn't even good. So what I'm trying to say is that you can plug in the debiased Whittle and you can sample with your favorite sampling technique and get the posteriors. What you'll notice is that if you see in blue, this is the debiased Whittle, and the true is the blue. Sorry, the green is the debiased Whittle, the blue is the true likelihood. While the green, the debiased Whittle, eliminates a lot of the bias, right? Because the Whittle likelihood underestimates this rho parameter. This is just for some simulated data, and it underestimates the sigma parameter. You're not going to get a good approximation of the true likelihood either way. And while it debiases it, you get better estimates in the frequentist sense. It's not straightforward how to make this Bayesian, right? Because that's what we want to. That's the question, the research question. Okay, and essentially what we want is we want proper uncertainty quantification. Okay, and at its heart, that's what Bayesian inference is. It's about finding the uncertainty of the parameters or of the model, given the data you've observed. And so let's just define the unnormalized posterior, the debiased Whittle. Right here, I'm just replacing true likelihood with the debiased Whittle likelihood. And I'll define this set coverage. So this posterior coverage, again, we have this posterior coverage function, which is the function of the data and some nominal interval alpha. Okay, conditional on the data, then the posterior coverage set is whether the parameters of the posterior within this interval, right? So think about a Bayesian credible interval, is equal to the nominal coverage you assume. So this is with respect to the posterior. Okay, and from this Monahan and Bruce paper from the 90s, what they argue is that if you want proper uncertainty quantification, then we want to make sure our posterior is valid by coverage. And you can see that here we've conditioned on the data. We're saying, given all possible data sets, right? As long as if we can simulate data, then we can do this many times, and then we can sample the posterior from that specific data, and then we can compute the quantiles, right? And then this should equal the nominal set alpha. So we want proper coverages in the Bayesian sense, and we do that by averaging over the parameters from the prior as well. So we'll get to that soon. Okay, so in these 2 slides, I've told you that, okay, I've just given you a way to that, okay, I've given you the goals that we want to make proper uncertainty quantification. And I've told you how to verify. So it's quite easy to verify, which we'll see in the next slide, but I haven't told you exactly how to do that with the debiased Whittle because we haven't done anything to the debiased Whittle yet. Okay, but to verify this, again, here's denoting the differences, right? The frequentist region is just when you condition on theta, right? This is a confidence interval, and a Bayesian credible interval is when you condition on the x's. Okay, And again, we can verify the validity or kind of the valid, if a posterior is valid by coverages, i.e. has proper uncertainty quantification through this simple algorithm given by Monahan, which is you take the prior, you simulate parameters from the prior, you simulate data conditional on the parameters, you sample the posterior given that data set you've simulated, and then you compute the quantiles. And this should be uniformly distributed. So this is a nice simple way to validate if your posterior has proper coverages. And so again, I've told you how to validate things. If you just read those papers, it's straightforward. But then the idea is, how do we still have to, if we just chuck the debiased Whittle in there, you won't get correct coverages, which we'll see. But the solution I've said on this slide is that we want to perform some adjustment to the debias, some curvature, i.e. we want to kind of inflate this variance of the debiased Whittle to account for and to obtain proper uncertainty quantification. Okay, so just going back briefly, we'll show you how to adjust that. So if we obtain the maximum likelihood estimate of the debiased Whittle, of course, we just maximize or minimize the likelihood. And it turns out that actually the debiased Whittle is in the framework of these estimating equations, i.e. it's a composite likelihood. If you've done any of that stuff, you would know that the composite likelihood is a misspecified model, but it has nice properties for its MLE. And in finite samples, what you'll see is that the variance of the maximum likelihood estimate of the debiased Whittle is in the form of this sandwich estimator. And the idea is that from this Rivertat paper, is that even though the MLE has the variance of this sandwich estimator, the curvature of the posterior is not. So essentially what we're saying is that the posterior itself is overconcentrated, but the variance of its MLEs is not. So what this paper does, this Rivertat paper here, is that we correct for this over concentration by using this so-called curvature adjustment. And the idea, we don't have to go through the specific details, but the idea is that we define this curvature adjusted likelihood, where essentially the theta star is what you evaluate, that's the maximum likelihood estimator. The C matrix is kind of the matrix the adjustment matrix. The theta is the one you've proposed. And again, this theta here is the maximum likelihood estimator. So the idea is that asymptotically you can correct for this, and we can actually get proper from the bursting on misses, or just from asymptotically, we can see that we actually get the sandwich estimator variance for the posterior, which is what we want. So this is, again, this is just a way to correct the curvature of this likelihood to at least asymptotically get proper uncertainty quantification. Okay, and that's all good. Like, that's one paper, so you just apply that for this debiased Whittle and you call it a day. But the issue again is that for many of these quantities, right, because this H matrix is actually, right, is the expected Hessian, and the J matrix is the variance of the score function. So it's not like, so the issue and the main contribution of this paper, even though we don't have to go over it, we don't have to bore you with the details, is that we actually estimate these matrices. Okay, so we estimate these matrices. First, you can estimate the sandwich estimator by simply estimating its inverse, by simulating these MLEs at the MLE of the data set, or we can just estimate the variance of the score, this J matrix, by, again, simulation. So we're doing Monte Carlo estimates of these adjustments, and this will get us at least an estimate, a consistent estimator of this adjustment matrix C. Because once we have the adjustment matrix, then we can get proper coverages, at least asymptotically. Okay, and the nice thing is, once you've done this, so it's a bit of kind of pre-processing. You have to compute the C. We propose two estimators, so C1 and C2. It's just a bit of pre-processing. Once you've computed C1 and C2, use your favorite sampling algorithm, MCMC algorithm, and then you can sample the adjusted Debiased Whittle posterior. Okay, and again, like I said before, here is the simulations to verify that these posteriors have proper coverages. So you can see that the unadjusted Debiased Whittle, you can see that this should be uniform, right? So you take a parameter from the prior, you simulate the data based on that parameter, and then you compute the posterior, and then you compute the quantiles. And those quantiles should be uniform. So you can see that as the grids increase, right, going from left to right, that the unadjusted Debiased Whittle does not have correct coverages, has this S shape. But when we make these adjustments, the C2 and C1, they're estimating the same thing. You can see as we increase in grid sizes, they become more uniform. So at least asymptotically, we can see that these actually provide the correct coverages under a certain prior. This is one specific prior. Here's another example. So this example is when we have random fields, but we have with missing data. So I think roughly 20 or 30% of the field was missing. And then we can still compute these quantities, and then we can make this adjustment. I think this is on a 512 by 512 grid size for the squared exponential kernel, I believe. And so you can see that making this adjustment is important because now it can provide corrected adjustments or corrected variances for this posterior. So that's important for this correct uncertainty quantification. Okay, so again, let's go back to the examples. So here's the sea surface temperature example. Okay, here's our data. It's on a 75 by 75 grid of latitude and longitude. Again, sea surface temperature over the Pacific Ocean. Okay, what we've done is we've compared three methods. So the standard Whittle, the Debiased Whittle, and the adjusted Debiased Whittle. Again, this is the kind of data after we've cleaned it, standardized it, things. This is the data we're going to estimate. And we're going to use the Maternity kernel. And so here are the marginal posterior. So again, three parameters, rho, sigma, nu. Okay, you can see in green, the Whittle, still underestimating this rho parameter. In blue is the Debiased Whittle. So it corrects this, it corrects the bias, right? It debiases the estimates. But the orange is the adjusted Debiased Whittle, which is essentially inflating the variance in a way to give proper coverages. Okay, and then this slide, what we did essentially, this is more of a sanity check, right? So we've looked at the Debiased Whittle estimate, okay, the mean, and we've looked at the standard Whittle, and we said, okay, let's use the mean of those parameters and simulate a random field and see what kind of covariance structures we get as a sense check. So we're just simulating you. So it's kind of like a posterior predictive check in a way. We're just simulating data based on the mean of the posteriors for each of these methods. You can see the real data is this on the left. The Debiased, you can see it still has very similar covariance patterns, structures. This is different. The data is not the same, but the covariance structure is closely matching. And you can see that the standard Whittle, because of this underestimate of rho and sigma, you can see, and the nu, you can see that it's very finely grained, the standard Whittle. So at least kind of as a one-off sense check, it's a good way to see if our Debiased Whittle is giving us kind of good estimates. Okay, and then here's our last example. Again, this is this photosynthetically active data. So again, this is radiation data. This is the same picture you've seen in the first slide. This is radiation between 400 and 700 nanometers. It's on a 120 by 100 precise grid of latitude and longitude. So this is only over a specific place over the coast of Baja, California. And again, so we have two types of missing observations. We have the land, that's in white. Okay, this is the actual land of California. And we have the cloud, the missing values due to cloud cover. So that's all in black. And the idea is that we want to make predictions about this missing data. Predictions or interpolations, right? And here we use an exponential covariance kernel. And again, we'll compare these methods. So for the marginal posteriors, again, in orange is the Whittle. Okay, we still get this kind of underestimated. It's low estimates of rho and sigma. The Debiased Whittle in green, and you can see that the adjusted, this is all done on the log scale, so you exponentiate, but you take this and the adjusted C1 and C2 these proposed adjustments, you can see that they've inflated this variance in a way. Okay, and then just for the, here's three draws, so three independent draws from the predictive distribution from the posterior. So here we're conditioning on the data you've observed, right? Remember the triangular region was missing. You've conditioned on the data, and you've conditioned on the parameter from the MCMC chain. And then we've simulated three different draws from the predictive distribution. So you can see that it'll give you different kind of predictions, but again, this is a way to look at the uncertainty in the missing data. Okay, and then just for future research, so hopefully the paper on arXiv will be out soon. We can again extend this to spatiotemporal models. We can also do anisotropic covariance functions. So I think one of our co-authors has done some work on these two. The original idea for this paper, but it turned out to be quite hard, was trying to subsample large spatial data. Okay, this is hard because you can't compute the expected periodogram you have to use the whole spectrum to compute the expected periodogram. So subsampling turned out to be quite difficult. And also for irregularly spaced data. So here we've assumed it's all on a grid and a rectangular gridded structure. But again, you can, there's been some work for irregularly spaced data, which is something for future research. Cool, so thanks for listening, everybody. Here's my bibliography of references. And any questions?